Right, we're doing refraction on a plane surface and refraction and internal reflection in fibre optics. So, refractive index. Light changes speeds and bends when it passes from one medium to the next. This is called refraction. So it's when a light goes like straight down, and then when it's inside a box, it does the ting, then it does the ting. The change of speed. When light passes from one medium to the next, it changes speed. In a vacuum, it travels at 3 times 10 to the 8 meters per second. But in all other materials, it goes slower. That because it has particles that it has to actually get through. The refractive index, N, of a material is the ratio of the speed of light in a vacuum and the speed of light in the material. Speed of light over speed of material as a refractive index. Right, we should probably read the next bit. So refraction index of air. Air contains lots of chemicals and elements such as oxygen and nitrogen. However, the speed of light in air is so close to the speed of light in a vacuum, you can approximate it to be the same. Therefore, the answer is 1. So refractive index, what colour corresponds to the speed of light in a vacuum? That is C. And CS is the one in different materials. Which of these statements about refractive indexes is true? Refraction is when light bends and changes speed. Refractive index of air is approximately 1, and it can never be less than 1, because I can explain that because it's simple maths. That's because obviously this is the speed of light, and it will always be slower than the speed of light, and any number divided by a number which is smaller than it will give a bigger number in return. No. Or any decimal number, which this is. Snell's law. Snell's law relates to refractive indices to an angle of incidence and refraction. So that is n1 sine x1 equals n2 sine x2. So basically, the refraction of this will be equal to the refraction of this. So, the ray of light begins in a medium with refractive index n1. Theta 1 is the angle of incidence here. N2 is the refractive index of the medium the light passes into, so this one. And O2 is the line of refraction, angle of refraction. So direction of bending. When light travels from a less optically dense medium to a more optically dense medium, it bends towards the normal. So the normal is obviously this line. So say it's coming in from this, it would bend that way towards the normal, so the angle wouldn't be as big. But if it's travelling from a more optically dense material to a less, it will move further away. So it could go like that, and then it could just yank off over there. The more optically dense material a medium is, the slower light travels through it. So what's the correct equation for Snell's law? Theta 1 is that one. N1 sine theta. When light travels to a more dense medium, it bends. It's not towards, it's away. Towards, oh no. More dense towards, less dense away. When light travels from a medium with a high refractive index to a medium with low refractive index, the critical angle is entirely reflected. So the critical angle is when sine C equals N2 over N1. So N1 is the more optically dense material, and N2 is the less optically dense material, so this and this. So total internal reflection. The angle of incidence is equal to the critical angle. That's when no light is refracted. Instead, it's reflected. This calls internal reflection. So that is when this angle of incidence is the same as the angle of reflection. So total internal reflection occurs when light is inside a more dense material and reflects off the boundary with a less dense material. Simple. What is the name for the angle at which a incidence ray is totally reflected? Critical angle. So what is the refractive index of a medium which is travelling at that? So that's C over c2. So that is the speed of light divided by 1.875 to the 7. So that would be 3 divided by 1.875. So that would be 16. Yep, it would be. So, refraction. Light travels at different speeds in different densities of materials. Light travels something in a less optically dense, and faster light bends away from the normal. At angles of incidence only equal to the critical angle. What? That just doesn't. At angles of incidence, something the critical angle, no light is reflected, so larger than or equal to. Yeah, that was so confusing because that just wasn't English. That was some other made-up Juju language. So Nambia, it's a weird African place. Hello, we're gonna move on, and we're moving on to internal reflection and fibre optics, which would have been lovely to know before we started answering questions on internal reflection. So internal reflection and the total internal reflection. Light speeds up when entering a less optically dense medium. When this happens, some of the light is refracted and some light is reflected. This is called internal reflection. If the angle of incidence is the same as the critical angle, light will travel along the boundary for the two mediums. If the angle of incidence exceeds the critical angle, then all light will be reflected. This is called total internal reflection. Okay. So, angle of incidence is the same as the critical angle. The light will travel along the boundary, so it will just travel along. And if it's bigger than the critical angle, all of it will be reflected, which is total internal reflection. So what are the conditions? Critical angle is exceeded, and the medium is entering with a low optical density. Optical fibers transmit light by total internal reflection. Small critical angle. Only light approaches the boundary at an angle that's very close to the normal, 90 degrees. Will cross the boundary and be refracted. Cladding. Each fibre has a core of optically dense material that is covered by a layer of cladding with a much lower optical density. This means that the boundary between the two materials has a very small critical angle, and long distances, these can continue over very long distances. So, what are the key features? Distance. Let's go say cladding. Cladding, protective coating, and the core. I would say let's watch. Actually, should we watch the video? What is the video on? Let's find out. Give me a second. Yeah, the video literally said what we've been saying, that like in fiber optic cables, if the cladding wasn't there, or the protective outer shell, then it wouldn't work because the overall thing wouldn't be going from a less dense to more dense substance. So pulse broadening and absorption. Pulse absorption can result in loss of signal intensity. Pulse broadening can degrade the signal. Pulse broadening. Material dispersion. Material dispersion is due to different wavelengths of light arriving at the end of fibers at different times. This is because the refractive index of the fibers change with frequency. This results in the pulse being broadened. The consequence of this is that the signal is now degraded. Signals may now overlap with each other, and to avoid material dispersion, monochromatic light could also be used. Monochromatic means the same wavelength. So pulse broadening, the model dispersion. Model dispersion is due to the different path signals that will take a fibre. This means different paths of the signal will arrive at different times. This results in the pulse being broadened. The consequence of this broadening will mean that the signal would now be downgraded. Signals now overlap with each other, and a monomode fibre can be used to stop this. Pulse absorption. A signal may be absorbed by a material. This would cause a reduction in the signal's amplitude, and countering signal degradation. Signals can be boosted by repeaters and counteract the effects of absorption and broadening. So why is cladding used? to be able to stop the signal reducing intensity, to reduce signal intensity, to reduce spreading. Yep. So if a material absorbs some light, it reduces the strength of the signal. If the material, it reduces the what could it reduce? It reduces amplitude of the signal. So what happens when a critical angle is exceeded? So when it is up, then all the light is reflected. When it's not exceeded, then it doesn't. So there is a protective coating on fibre optics. There's a core and there's cladding. Perfect. And if light pulses something out too much, then they may blur into the next pulse, which would something the signal. If light pulses something out too much, then might blur into the next pulse, which would distort the signal. If light pulses refract, nope, spread out too much. That's the same thing. What is the phenomenon that occurs when light is incident at an angle greater than the critical angle on the reflection, or total reflection, total angle reflection? Pretty sure that's what it is. It is total. What is it? It's total. That's reflection. Total phenomenon. Internal. Total internal reflection. Perfection. So some examples are cables and optical fiber cables. This we have literally just done. Optical fiber uses total internal reflection. Perfect. Done. Peace.